Okay, this video is going to be for section 3.6, finding or converting from the general form to the vertex graphing form in the quadratic equations. So going from general form to the vertex graphing form. And we're specifically going to look at a few examples here, but in this tutorial we're going to look at only when x squared when the x squared term has a 1 coefficient for it. So this is what we would do. Let's say we have an example here. And we want to graph this and state the vertex points, the axis of symmetry, and everything else that would go with a quadratic equation. Intercept points or whatever. But we're going to graph this. So what we have to do is we have to complete the square to put this in the vertex graphing form. So completing the square means that we have to always look at the x term and what the coefficient is in front of the x term. We take half of that and we square it. And this will give us a number to add in to make a trinomial that will give us a perfect binomial square when we reduce it down. So this would be equal to x squared plus 8x. So 8x is half of that is 4. 4 squared is 16, so add 16. And add the 19 in there. I tend to bracket this up so that we know that that's our trinomial. Now the one thing you can't do here is you can't leave it like that. You also, because you added 16 to your question, you have to keep the equation the same. So you have to also subtract it out here. So also don't forget to subtract. Okay, because we're not subtracting over here or adding it over here to keep it the same, so we have to subtract it over here to keep this the same. So now we can just convert it to the vertex graphing form. Okay, so that would mean, well, this would convert down into a binomial, x plus 4 all squared. If you expand that out, it gives us what's in brackets above here. Then we could combine these to get plus 3, and this would give us our vertex graphing form. We now know that a is 1, p is negative 4, and q is 3. So a equals 1, p equals negative 4. Remember, there's always that negative in there, so it has to be the opposite sign. And q is equal to 3. So we know our vertex is equal to negative 4 and 3. Our axis of symmetry is x is equal to negative 4. And we're going to draw this out now. I'm going to slide this up into the field of view so that I can draw the graph. So when I do this one, it's going to have a lot of upper area to it. So I'm going to put my graph way down here like this. My x-axis is going to be way down here. Sketching the graph. So this is my x-axis and this is my y-axis. This will help us to draw the graph. So what we do here is we put the vertex point down. Vertex we know is negative 4 and 3. Negative 4 and 3. There's our vertex point. Our axis of symmetry is x equals -4, so that would be this. I'm going to put a dotted line for that. And we know that if we were going to try to find the x-intercepts here, we would know that because a is a positive value, +1 out there, there's no, it's going to be moving upwards like this. So that means we will not have any x-intercepts, no x-intercepts. Because it's curving up like this. So what we'll do is we'll find the y-intercept here, and then we'll use the axis of symmetry and find the point that would be the mirror point on the other side of it to find 2 points to draw our curve. So to find the y-intercept, that means x is equal to 0 at that point. So we would just go y is equal to 0 plus 4 all squared plus 3. So that's 16 plus 3 is equal to 19. So let's find 19 on here. That's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. All the way up there. So I would do this to find the actual mirror point on the other side. We would just simply take the axis of symmetry here, and I'm going to extend it a bit, and look that this point is 1, 2, 3, 4 to the right of it. So we go 4 to the left and put another point. 1, 2, 3, 4 at the same level. 1, 2, 3, 4. So there's 2 points to draw our curve with. We could check down here if we wanted to find some more, but this would be enough to draw the graph here. And it's going to be of normal thickness because of a being 1. So I'm just going to try to eyeball here like this. Kind of missed that one a little bit. So this is my quadratic equation graph. X-intercepts, there are none. If there was x-intercepts available here, say it went downwards, we would have to substitute y is equal to 0 in and solve for the possible x-intercepts that could happen there. Okay, so here's my graph. Here's my axis of symmetry. Here's the vertex. So I'm going to label the vertex. I'm going to label the graph. And the axis of symmetry. I'm just going to put sim in there. And that would be an example of doing a conversion where you just have x squared has a coefficient of 1. In our next tutorial, we're going to look at a little more complex example when those x squared coefficients are a little higher.